The night sky is lying to you. Every time you look up and see darkness between the stars, you're staring at something that, according to the laws of physics, should not exist. That darkness between the stars is not empty. It never was. It's something we can't detect, can't explain, and genuinely cannot stop. And here is a question. If you could break one law of physics for a day, which would it be? And what would you do? Let me know in the comments. I will pin the most creative answer. Now let's begin. Picture this. The universe is enormous, beyond anything your brain is actually built to comprehend. There are more stars out there than grains of sand on every beach and every desert on the entire planet Earth. Some estimates put the number somewhere around 2 sextillion. That's a 2 followed by 21 zeros. These stars are scattered across hundreds of billions of galaxies, spread out across space in every direction you could possibly look. If there are that many stars in that many directions, then why do you see mostly nothing? Think about it carefully. If the universe were infinite and filled with stars in every direction, then every single line of sight, no matter where you pointed your eyes, would eventually land on the surface of a star. Every direction would end in fire. The entire sky should glow as brightly as the surface of the sun, not just in spots, everywhere, all the time, day and night, but it doesn't. And that gap between what the math says should happen and what you actually see when you step outside on a clear night. That gap has a name. Scientists call it Olbers Paradox. It's named after a German astronomer named Heinrich Wilhelm Olbers, who wrote about it formally in 1823. But the question itself is older than that. Johannes Kepler, the astronomer who figured out how planets orbit the sun, raised a version of it all the way back in 1610. Even Edgar Allan Poe, yes, the man who wrote The Raven and the Telltale Heart, took a serious scientific swing at solving it in an essay called Eureka, published in 1848. This darkness has been pulling at curious minds for a very, very long time. And the answer, the real scientifically verified answer we have today, is not simple, it's not comforting, and once you understand it, the night sky will never look the same to you again. To understand why the sky is dark, you first have to understand something that took humanity a surprisingly long time to accept. The universe did not always exist. Roughly 13.8 billion years ago, everything, every single atom, every particle of matter, every force of nature, every dimension of space and every tick of time exploded into existence from an unimaginably hot and dense starting point. We call it the Big Bang, and while that name might sound almost casual, what it actually describes is the most extreme event in the history of reality. In the very first fraction of a second, the universe expanded at a rate that makes the human imagination buckle. Space itself stretched outward faster than the speed of light, not because anything was physically traveling through space faster than light, which would break Einstein's rules, but because space itself was growing. The universe wasn't exploding into some pre-existing empty room. There was no room. Space was being created as it expanded, carrying everything within it outward in all directions simultaneously. And it has never stopped now, because light travels at a finite speed, about 300,000 kilometers per second, or roughly 186,000 miles per second. There is a hard limit on how far we can see. If a star is so distant that its light hasn't had enough time to cross the space between us in 13.8 billion years, then that star is simply invisible to us. It sits beyond what astronomers call the cosmological horizon. The universe we can actually observe, detect, measure, and study forms a sphere roughly 93 billion light-years across. And beyond that boundary, we genuinely don't know what's out there. Not yet. Maybe not ever with our current tools. So the first reason the sky is dark is simply this. The universe is not infinitely old, and light from the most distant stars hasn't had enough time to reach us. The darkness you see on a clear night is, in a very real sense, the universe showing you its own age. It's a clock, a vast cosmic timestamp written in the absence of light, but that's only part of the answer. Because there's another layer beneath it, and this one is where the story tips from beautiful into something far more unsettling. In 1998, two completely independent teams of astronomers set out to answer what seemed like a fairly straightforward question. How fast is the universe's expansion slowing down? Notice the assumption in that question. They weren't asking if it was slowing down. They were asking how fast. It seemed obvious that it should be slowing down. Gravity pulls matter together. The combined gravitational pull of every galaxy, every star, every atom in existence should act like a hand pressing down on the brakes, gradually reining in the expansion that started with the Big Bang. Eventually, some scientists thought gravity might even reverse the expansion entirely, pulling everything back together in what they called the Big Crunch. To measure this deceleration, both teams studied a very specific type of exploding star called a Type Ia supernova. These are remarkable objects. They always explode with nearly the same intrinsic brightness, which makes them extraordinarily useful as measuring tools. Astronomers call them standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate exactly how far away it is. Brilliant, elegant physics. What both teams expected to find was that the distant supernovae were slightly closer than a constant expansion model would predict. Confirmation that gravity was doing its job, pulling the brakes. What they actually found stopped them cold. The supernovae were dimmer than expected, not brighter, dimmer, which meant they were farther away than the models predicted, far farther. The expansion of the universe wasn't slowing down at all, it was accelerating. Something, some unknown force filling all of space, was not just resisting gravity, it was overwhelming it, pushing everything apart. Faster and faster, this discovery was so staggering, so completely at odds with everything cosmologists had assumed, that the team spent years rechecking their data before announcing it publicly. And when they finally did, it changed everything. In 2011, the scientists who led those teams, Saul Perlmutter, Brian Schmidt, and Adam Riess, were awarded the Nobel Prize in Physics for the discovery. We gave that unknown force a name, dark energy, and according to the best measurements we have today, it makes up roughly 68% of the total energy content of the entire universe. Dark matter, another mysterious substance we've never directly detected, makes up about 27% more. All the atoms, stars, planets, moons, galaxies, gas clouds, black holes, and every single thing you've ever seen, touched, or imagined. All of that ordinary matter accounts for less than 5% of everything that exists. We are not the main characters of this universe. We are a footnote, a thin layer of complexity floating on top of a reality we barely understand. Now here is where the darkness becomes truly terrifying. Because if dark energy keeps doing what it's doing, and every observation we've made suggests it will, the universe is on a path toward a kind of darkness so complete, so absolute, that no amount of stars will be able to fight it back. Not because the stars will burn out, but because the expansion of space will carry them beyond reach, one by one, like lights being switched off in a room you can never leave. Galaxies that are currently visible to us will eventually recede so fast that their light will never reach us again. They'll cross our cosmological horizon and simply cease to exist from our perspective. The universe will grow quieter, emptier, darker. Not in some distant abstract future. This process has already started. Some galaxies are already beyond our reach, already accelerating away from us faster than light can bridge the gap. And here's the question that should be echoing in the back of your mind right now. If the darkness is already spreading, how much time do we actually have, and what happens when it's complete? We're going to get into exactly that. including what astronomers have found when they pointed the James Webb Space Telescope at the oldest light in the universe, and what it tells us about where all of this is heading. So we left off with something quietly terrifying. The universe is not just expanding, it's accelerating outward, driven by a force we cannot see, cannot measure directly, and cannot fully explain. And the darkness you see when you look up at the night sky is not just an absence of light. It is a symptom, a visible sign of something much larger happening to the fabric of space itself. But before we zoom all the way out to the end of everything, I want to bring you back to something a little closer. Because the darkness of deep space isn't just a future problem. It's a present one. And in the last few years, we've gotten some of the most breathtaking and deeply strange views of it that humanity has ever seen. On July 12, 2022, NASA released the first full-color images from the James Webb Space Telescope. If you haven't seen them, I genuinely encourage you to look them up after this video. They are some of the most extraordinary photographs ever taken by human beings. One of the first images released was called Webb's First Deep Field. It showed a galaxy cluster known as SMACS 0723, located about 4.6 billion light-years from Earth, and packed into a patch of sky roughly the size of a grain of sand held at arm's length were thousands upon thousands of galaxies, some of them ancient almost beyond comprehension. Some of them so far away that the light reaching Webb's mirrors left those galaxies when the universe was less than 1 billion years old, when the cosmos was still in its infancy, still figuring out what it wanted to be. What makes Webb so powerful is its ability to see in infrared light. The universe is expanding, and as it expands, it stretches the wavelength of light traveling through it. Light that started out as visible or ultraviolet radiation gets stretched, redshifted astronomers call it, into the infrared range over billions of years of travel. Our eyes can't see infrared. Neither could the Hubble Space Telescope, at least not at the depth Webb can reach. But Webb was designed specifically to capture this ancient, stretched light. It is, in a very real sense, a time machine. Every image it captures is a window into the deep past, and what Webb found in that deep past has raised some fascinating and genuinely puzzling questions. One of the biggest surprises from Webb's early observations was the discovery of galaxies that looked far too mature for their age. In the very early universe, within the first few 100 million years after the Big Bang, you wouldn't expect to find large, well-formed, structured galaxies. The conventional model of cosmic evolution says that galaxies grow slowly, over billions of years, by pulling in gas and merging with smaller structures. Building something large and organized takes time. But Webb kept finding galaxies that looked ancient even when the universe was young. Massive, structured, surprisingly bright galaxies sitting at redshifts that placed them incredibly far back in time. Some of these galaxies appeared to contain as many stars as the Milky Way does today, yet they existed when the universe was only a few 100 million years old. That timeline, according to the standard model, barely leaves enough room for those galaxies to have formed at all, let alone grown that large. A study published in early 2023 in the journal Nature Astronomy described 6 candidate galaxies so massive and so ancient that one of the researchers, astronomer Ivo Labi, compared their existence to finding a dinosaur in a world that supposedly hadn't evolved past single-celled organisms yet. The numbers, he said, simply didn't add up. Now, and this is important, science is an ongoing process. These findings don't necessarily mean the Big Bang model is broken. They might mean our understanding of how quickly galaxies can form needs significant revision. They might point to new physics operating in the early universe. They might even be partially explained by active galactic nuclei, supermassive black holes at the centers of these galaxies, pouring out enormous amounts of energy and light, making them appear more massive than they actually are? The honest answer is, we don't fully know yet. And that's not a weakness of science. That's exactly what science is supposed to do. It finds the edges of what we understand and pushes outward. Every surprise is an invitation, but let's talk about the darkness itself again, because there's a layer to this story that most people never hear about, and it connects everything we've discussed so far in a way that I find genuinely haunting. When astronomers look out into deep space, really deep space, not just at nearby stars or even nearby galaxies, but at the vast stretches between galactic superclusters, they find something that should not surprise us anymore, but still somehow does every time. Emptiness, not just a little emptiness. Vast, almost unimaginable voids. Regions of space hundreds of millions of light years across, containing almost no galaxies at all. No stars, no gas clouds, essentially nothing. These regions are called cosmic voids, and they are among the largest known structures in the observable universe. The largest confirmed void we know of is called the Bootis void, discovered in 1981. It is roughly 330 million light-years in diameter. To put that in context, our entire Milky Way galaxy is about 100,000 light-years across. The Bootis void is so enormous that if the Milky Way were sitting at its center, we would have thought the universe itself was nearly empty. The nearest galaxies would have been so far away that for most of human history, we might never have detected them at all. We might have looked up, seen nothing, and concluded we were utterly, cosmically alone. There are astronomers who have half-jokingly and half-seriously suggested that structures like the Bootis void are so impossibly large that they strain the limits of what the standard cosmological model can explain. The universe should be somewhat uniform on the largest scales, the theory says. Gravity shouldn't have had time to create something quite that empty, quite that vast, and yet there it is, a hole in the universe 330 million light-years wide, sitting in the constellation Bootis, quietly refusing to be explained away. Now, if voids like that exist, regions of space so empty they make the rest of the universe look crowded, you have to ask the natural follow-up question, what's in them? Not the obvious answer of nothing, because nothing is rarely actually nothing in physics, and this is where things get deeply, philosophically strange. Space, even completely empty space, devoid of stars, galaxies, gas, dust, or any conventional matter, is not truly empty. According to quantum field theory, the framework of physics that describes the behavior of subatomic particles and forces, what we call empty space is actually a seething, roiling ocean of quantum fields. These fields fluctuate constantly, producing pairs of virtual particles. Particles and their antimatter counterparts that pop into existence and annihilate each other almost instantaneously. These are not hypothetical, they have measurable effects. They've been confirmed experimentally through something called the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a tiny but measurable attractive force caused by these quantum fluctuations in the space between them. This means that the darkness of a cosmic void is not passive, it is not simply an absence, it is a churning, dynamic, energetic nothingness, constantly producing and destroying matter at scales far too small for us to see, but real nonetheless. And here's the unsettling bridge between that quantum weirdness and the large-scale darkness we've been discussing. Many physicists believe that dark energy, that mysterious accelerating force driving the universe apart, may actually be related to this energy of empty space. It might literally be the energy of the vacuum itself, the sum total of all those quantum fluctuations in every cubic centimeter of space throughout the entire observable universe. If that's true, then the darkness that is pulling the cosmos apart, galaxy by galaxy, is coming from inside the house. It's woven into the structure of space itself. It cannot be turned off, shielded against, or avoided. It simply is. The universe is not falling apart despite the darkness. The darkness is the mechanism. There's one more idea I want to plant in your mind before we move into part 3, because it connects everything we've talked about: the finite speed of light, the expanding universe, the cosmic voids, the quantum vacuum, into a single staggering thought. Every time you look at the night sky, you are not seeing the universe as it is. You are seeing it as it was. The light from our nearest stellar neighbor, Proxima Centauri, takes about 4.2 years to reach us. When you look at it, you're seeing it as it existed 4.2 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, just barely visible to the naked eye as a faint smear of light in the constellation Andromeda, is about 2.5 million light-years away. The light you're seeing left Andromeda 2.5 million years ago, when our ancestors were still early hominids, probably carrying stone tools and looking up at a sky that already contained this same ancient light. The most distant objects Webb has photographed are over 13 billion light-years away. We are seeing them as they were 13 billion years ago. The galaxies we observe in those deep-field images may not even exist anymore. They may have merged, evolved, been torn apart, or transformed utterly in the billions of years since that light left them. We are not observers of the universe. We are archaeologists. Everything we see is a fossil, and the darkness between those fossils, the black silence stretching between the ancient lights, is not empty. It is full of things we cannot see yet, things moving away from us, carrying their light with them into the unreachable distance. That's the true face of the cosmos, and we're just beginning to understand it. Everything we've talked about so far, the darkness of the night sky, the accelerating expansion, the invisible matter woven through every galaxy, these aren't isolated mysteries sitting in separate corners of cosmology. They are all threads in the same fabric, and when you zoom out far enough to see the full picture, that fabric reveals a structure so vast, so intricate, and so unexpected that the scientists who first mapped it could barely believe what they were seeing. We call it the cosmic web. And it is, without any exaggeration, the largest known structure in the observable universe. To understand how the cosmic web came to be, you have to go back almost to the very beginning. Not quite to the Big Bang itself, that first incomprehensibly hot fraction of a second, but to a period shortly after, when the universe had cooled just enough for matter to begin clumping together under the influence of gravity. In the very early universe, matter wasn't distributed perfectly evenly. There were tiny quantum fluctuations, microscopic variations in density, the kind of random quantum noise we talked about in part 2 when we discussed the energy of empty space, and these tiny ripples were the seeds of everything that came after. Where matter was slightly denser, gravity pulled in more matter from the surrounding regions, making those spots denser still. Where matter was slightly thinner, it drained away toward the denser regions, leaving those spots emptier. Over hundreds of millions of years, this process of gravitational collapse amplified those tiny initial wrinkles into something enormous. The dense regions became filaments, long, thread-like structures of gas and dark matter stretching across hundreds of millions of light years. Where filaments intersected, matter piled up into massive nodes. Those nodes became galaxy clusters, the densest, most gravitationally bound structures in the cosmos. And the regions between the filaments, they became the voids, those vast, almost empty bubbles of space we explored in part 2. The result is a structure that, when visualized in 3 dimensions using data from large galaxy surveys, looks almost biological. It looks like a sponge. It looks like sea foam frozen at cosmic scale. It looks uncannily like the neural network of a brain, a comparison that has been made seriously by scientists. Not just as a poetic flourish, though we'll come back to that. The first time this structure was clearly observed was in the 1980s through a landmark project called the CFA Redshift Survey, carried out at the Harvard-Smithsonian Center for Astrophysics. By measuring the redshifts of thousands of galaxies, essentially mapping their distances from Earth, astronomers Margaret Geller and John Houtra produced the first real three-dimensional map of the nearby universe. What emerged from their data was a stunning revelation. Galaxies were not scattered randomly through space. They were arranged in enormous sheets and filaments, with massive empty voids between them. One structure in particular, a curved sheet of galaxies they called the Great Wall, stretched across more than 500 million light-years, the largest structure known at the time. Since then, our maps have grown dramatically. The Sloan Digital Sky Survey, which began collecting data in 2000, has mapped the positions of hundreds of millions of galaxies across a significant portion of the sky. The picture it reveals is breathtaking in its complexity and consistency. The cosmic web is real, it is everywhere. It is the fundamental architecture of the observable universe. And the filaments themselves, those vast highways of matter connecting galaxy cluster to galaxy cluster across hundreds of millions of light-years, contain most of the universe's ordinary matter in the form of warm, diffuse gas. For a long time, astronomers couldn't actually detect this gas directly. It was too diffuse to show up clearly in conventional observations, but it had to be there. Theoretical models demanded it. The problem even had a name, the missing baryon problem, referring to the fact that cosmologists could only account for about half of the ordinary matter the Big Bang should have produced, with the rest seemingly vanished. In 2020, two independent research teams, one using data from the European Space Agency's XMM Newton X-ray telescope and another using a technique called the kinematic Sunyaev-Zeldovich effect, which detects gas by the subtle imprint it leaves on the cosmic microwave background, finally confirmed direct detections of this warm, diffuse gas threading through the cosmic filaments. The missing baryons had been found, hiding in the vast, tenuous highways of the cosmic web all along. Another reminder that the universe rarely loses anything. It just puts things somewhere we haven't looked yet. Now, I mentioned earlier that the cosmic web bears a striking visual resemblance to a neural network, a brain, and I want to spend a moment here because this comparison deserves more than a passing mention. It deserves honest examination. In 2020, a paper was published in the journal Frontiers in Physics by Franco Vazza, an astrophysicist at the University of Bologna, and Alberto Felletti, a neurosurgeon at the University of Verona. They compared the large-scale structure of the universe with the structure of the human cerebral cortex, the thin outer layer of the brain responsible for thought, memory, and consciousness. Their analysis found remarkable quantitative similarities. Both systems contain roughly the same number of nodes, around 100 billion. Both show similar clustering properties. Both have similar fractions of their total mass and energy devoted to active components versus passive ones. The self-organizing dynamics that produce the cosmic web through gravitational collapse show mathematical parallels to the self-organizing dynamics of neural network formation. Now, and I want to be very clear about this, because honest science communication requires it, this does not mean the universe is conscious. It does not mean the cosmic web is a brain. It does not mean there is some cosmic intelligence thinking thoughts on a scale we can't perceive. The similarity is structural and mathematical. Two completely different systems, governed by completely different physics, arriving at similar organizational patterns because similar mathematical principles, network theory, self-organization, scale-free connectivity, operate in both domains. But here's what that finding genuinely does tell us. Complexity and organization emerge naturally from simple initial conditions and consistent physical laws. The universe doesn't need a designer to produce intricate, interconnected, almost impossibly beautiful structures. Given enough time, the right initial conditions, and the steady pull of gravity, the cosmos will organize itself into something that looks, to our pattern-seeking human minds, almost alive. That's not less wonderful than the alternative. It might be more wonderful. Let's zoom into one particular filament of the cosmic web, the one we actually live in. Our Milky Way is part of a gravitationally bound group of galaxies called the Local Group, which also includes the Andromeda Galaxy, the Triangulum Galaxy, and roughly 50 smaller dwarf galaxies. The Local Group itself sits near the edge of a much larger structure called the Virgo supercluster, which contains dozens of galaxy groups and clusters spread across about 110 million light-years. But in 2014, a team of astronomers led by Brent Tully at the University of Hawaii redrew our cosmic address entirely. Using a new technique to map the flow of galaxies through space, essentially tracking which direction everything is gravitationally falling toward, they identified a supercluster of galaxies so enormous that it redefines what we thought of as our cosmic neighborhood. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 520 million light-years and contains the mass of approximately 100 million billion suns. It includes the Virgo supercluster, which we previously thought of as our home supercluster, as just one small lobe of a much larger whole. At the heart of Laniakea, every galaxy in this vast structure is gravitationally falling toward a region of extraordinarily dense mass concentration called the Great Attractor. The Great Attractor is one of the more unsettling objects in cosmology. It is a gravitational anomaly located about 250 million light-years away, in the direction of the Centaurus and Norma constellations. Everything in our local cosmic region, the Milky Way, Andromeda, the entire Virgo supercluster, and hundreds of thousands of other galaxies, is being pulled toward it at speeds of hundreds of kilometers per second. And for a long time we couldn't even see it, because it sits almost perfectly behind the plane of our own galaxy, hidden behind the thick dust and gas of the Milky Way, in a region astronomers literally call the zone of avoidance. We are all falling towards something enormous that we spent decades unable to even look at directly. If that doesn't capture the spirit of this whole story, the darkness, the invisible forces, the structures hidden in plain sight, I'm not sure what does. The cosmic web, Laniakea, the Great Attractor, these aren't just abstract astronomical concepts. They are your address, your real, full cosmic address. You are not simply on a planet orbiting a star, you are on a planet orbiting a star, in a spiral galaxy, in a galaxy group, in a supercluster, in a vast gravitational basin, in one filament of a web that stretches across the entire observable universe. And every node of that web, every filament, every galaxy cluster sitting at those luminous intersections, they are all moving, they are all evolving, and they are all, slowly and inevitably, being pulled apart by that dark energy we talked about in part 1. The web is not permanent. Over timescales of tens of billions of years, the accelerating expansion will stretch the filaments thinner and thinner, dissolve the connections between clusters, and eventually leave each gravitationally bound group of galaxies stranded in an expanding ocean of emptiness, cut off forever from the rest. The cosmic web is one of the most beautiful things the universe has ever made, and it is temporary. But before we get to what happens at the very end of all of this, the ultimate fate of the universe, the final darkness, there's one more chapter we need to cover first, because sitting at the center of nearly every large galaxy in the cosmic web, including our own, is something so extreme, so violent, and so fundamental to how galaxies live and die that no story about the darkness of space is complete without it. There is an object sitting at the center of our galaxy right now. It has been there for billions of years, silent and patient, hidden behind a thick curtain of dust and gas that blocked our view of it for most of human history. It weighs about 4 million times as much as our Sun, and the space around it is so warped, so violently curved by its gravitational pull that even light, the fastest thing in the universe, the thing we've been talking about this entire time, cannot escape it once it crosses a certain boundary. We gave that boundary a name, the event horizon, and what lies beyond it is, in the most literal sense possible, unknowable. Not unknown in the way dark matter is unknown, where we simply haven't built a sensitive enough detector yet. Unknowable in a deeper, more fundamental way. The laws of physics as we understand them break down completely at the center of a black hole. Our equations produce infinities. Our models stop working. Whatever is actually happening in there exists outside the reach of any observation we could ever make, because no information from beyond that boundary can ever reach us. That's not a poetic exaggeration. It is a mathematically proven feature of general relativity, and it is one of the most profound and disquieting facts in all of science. Let's start with what a black hole actually is, because the word gets thrown around so casually that its true strangeness rarely gets the attention it deserves. A black hole is a region of space where matter has been compressed so densely that the gravitational field it produces curves space-time to a point of no return. The event horizon is not a physical surface. There is no wall there, no membrane, nothing you could touch or detect as you crossed it. It is simply the boundary beyond which the escape velocity, the speed you would need to travel to break free of the gravitational pull, exceeds the speed of light, and since nothing can travel faster than light, nothing can escape. Not matter, not energy, not information of any kind. The simplest way black holes form is through the death of massive stars. When a star significantly more massive than our Sun exhausts its nuclear fuel, the outward pressure that has been holding it up against its own gravity suddenly disappears. The core collapses in a fraction of a second, sometimes producing a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh about 10 billion kilograms on Earth. But if the collapsing core is massive enough, not even the quantum pressure of neutrons packed against each other can stop the collapse. It continues, past the neutron star stage, into a singularity, a point of theoretically infinite density wrapped in an event horizon. A black hole is born, but stellar mass black holes, the ones formed this way, typically ranging from a few times the mass of the Sun up to perhaps 100 solar masses, are not the most dramatic members of their family. Not by a long shot. At the center of nearly every large galaxy, including the Milky Way, sits a supermassive black hole. These are monsters of a completely different scale, ranging from millions to tens of billions of solar masses, and how they formed is still not entirely clear. They may have grown from the mergers of smaller black holes over billions of years. They may have formed from the direct collapse of enormous gas clouds in the early universe. They may have had a head start from primordial black holes, hypothetical objects formed in the extreme density of the very early cosmos before any stars existed. Most likely it's some combination of all of these processes, varying from galaxy to galaxy. The supermassive black hole at our galactic center is called Sagittarius A star, written as Sagittarius A, and for decades its existence was inferred rather than directly observed. We watched stars near the galactic center moving in tight, high-speed orbits around an invisible point, and the only object massive enough and compact enough to produce those orbits had to be a black hole. The evidence was overwhelming, but seeing it directly was another matter entirely. Then, in April of 2019, everything changed. The Event Horizon Telescope, not a single telescope but a planet-spanning network of 8 radio observatories, linked together through a technique called very long basiline interferometry to effectively create a telescope the size of the entire Earth, released the first ever image of a black hole's event horizon. The target was not Sagittarius A star, but a supermassive black hole at the center of a galaxy called Messier 87, or M8A7, located about 55 million light-years away. The black hole itself has a mass of approximately 6.5 billion suns. The image that appeared on screens around the world on that April morning was a glowing orange ring, the superheated accretion disk of gas and dust spiraling into the black hole, bent and brightened on one side by the black hole's rotation, with a dark central shadow marking the event horizon itself. It was blurry by the standards of most astronomical photographs, but what it represented was extraordinary. For the first time in history, a human being could look at a picture and say, "There is the edge of a black hole. There is where the known universe ends." 3 years later, in May of 2022, the Event Horizon Telescope team released a second image, this time of Sagittarius R star, our own galactic center. It showed the same characteristic glowing ring, the same dark shadow, but capturing it had been significantly harder. Because Sagittarius A star is much smaller and its surrounding gas moves much faster, completing orbits in minutes rather than weeks. The image was constantly shifting during the observation period, like trying to photograph a child who won't sit still. The final image required sophisticated new computational techniques to reconstruct. But there it was, the darkness at the heart of our own galaxy, rendered visible for the first time. Now, here's where the story of black holes connects back to the story of cosmic darkness in a way that most people never think about. Black holes seem, on the surface, like ultimate devourers, objects that consume everything and give back nothing. But in 1974, a physicist named Stephen Hawking published a calculation that turned that intuition upside down, and in doing so, planted one of the deepest unsolved problems in modern theoretical physics right at the intersection of quantum mechanics and general relativity. Hawking showed that black holes are not completely black. They glow, very faintly, very slowly, but they emit a continuous thermal radiation, now called Hawking radiation, caused by quantum effects at the event horizon. Here's how it works, in the most accurate, simplified version I can give you. Remember those virtual particle pairs we discussed in Part 2, the quantum fluctuations of empty space, where pairs of particles and antiparticles constantly pop into existence and annihilate each other. At the event horizon of a black hole, something different can happen. If a virtual particle pair forms right at the boundary, it's possible for one particle to fall inward past the event horizon while the other escapes outward into space. The escaping particle becomes real. It carries away real energy, real radiation, and the energy for that radiation comes ultimately from the black hole itself. The black hole loses mass, slowly, imperceptibly slowly for large black holes, but steadily, irreversibly. This means black holes evaporate. Given enough time, an almost incomprehensibly vast amount of time, every black hole in the universe will radiate away its mass completely and disappear in a final burst of energy. A stellar mass black hole might take around 10 to the power of 67 years to evaporate. A supermassive black hole like the one in M87 would take something in the neighborhood of 10 to the power of 100 years. To put that in perspective, the current age of the universe is roughly 10 to the power of 10 years. The timescales we're talking about are so astronomically larger than anything we normally consider that our language doesn't really have adequate tools to express them. But here's the problem, and it's a problem so deep that it has consumed some of the greatest minds in theoretical physics for 50 years. When matter falls into a black hole, it carries information. Not just mass and charge, but the specific quantum state of every particle, which way its spin was oriented, what its momentum was, every detail of its physical configuration. Quantum mechanics has a rule, a foundational, non-negotiable rule: that information cannot be destroyed. The total quantum information content of the universe must be conserved. This is called unitarity, and it is one of the bedrock principles of quantum theory. But if a black hole evaporates completely into Hawking radiation, which is, according to Hawking's original calculation, completely thermal and random, containing no information about what fell in, then all that information is gone, destroyed. The universe has lost something it can never recover. This is the black hole information paradox, and it represents one of the sharpest conflicts in modern physics, a direct collision between general relativity, which produces black holes and event horizons, and quantum mechanics, which forbids the destruction of information. Both theories are extraordinarily well tested, extraordinarily precise, and extraordinarily successful in their own domains. And they flatly disagree about what happens to information that falls into a black hole. Hawking himself spent decades wrestling with this paradox, changing his position multiple times. In 2004, he conceded that information is probably not destroyed, that it must somehow be encoded in subtle correlations within the Hawking radiation, in a way his original calculation had missed. But the precise mechanism, how exactly the information escapes, how it gets encoded in radiation coming from a region where quantum effects and gravity both operate at their most extreme, remains deeply unclear. In recent years, physicists have made some tantalizing progress using a framework called the holographic principle, which suggests that the information content of a region of space can be fully described by a lower dimensional surface surrounding it. Like how a three-dimensional object can cast a two-dimensional shadow. Applied to black holes, this suggests the information falling in might be somehow encoded on the event horizon's surface itself and gradually released through the Hawking radiation as the black hole evaporates. A 2019 paper by Ahmed Al-Mhairi and collaborators, building on what's called the island formula, showed that under certain assumptions, the Hawking radiation does eventually carry out the information, but the full solution, especially in our actual four-dimensional universe with actual gravity, remains incomplete. The information paradox is not just a technical puzzle about exotic objects. It's telling us that our two greatest theories of reality are fundamentally incompatible, and that somewhere in the gap between them lies a deeper theory, a theory of quantum gravity that we have not yet found. There's one more aspect of black holes I want to leave you with before we move forward, because it reframes everything we've discussed in a way that genuinely moves me every time I think about it. Black holes are not just destroyers. They are, in a very real sense, among the most creative forces in the universe. When a supermassive black hole is actively feeding, pulling in gas from its surrounding accretion disk, it releases an enormous amount of energy in the form of jets of plasma and radiation blasting outward along its rotational poles at close to the speed of light. These jets, called relativistic jets, can stretch for millions of light years and pour more energy into their surrounding environment than hundreds of billions of ordinary stars combined. The black hole at the center of a galaxy called M87, the same one the Event Horizon Telescope imaged, has a jet extending about 5,000 light-years, which was actually detected and photographed long before the black hole's event horizon was imaged. These jets and the intense radiation from actively feeding black holes, objects we call quasars or active galactic nuclei, have a profound effect on the galaxies surrounding them. They heat the surrounding gas, blast it outward, suppress star formation in some regions while triggering it in others. They regulate how galaxies grow. They prevent galaxy clusters from cooling and collapsing into runaway star formation. Without the feedback from supermassive black holes, galaxies would look very different, possibly hostile to the kind of stable, long-lived stellar environments where planets like Earth can form. The darkness at the center of our galaxy, the invisible monster around which hundreds of millions of stars orbit, may be partly responsible for the fact that our galaxy is a place where life could arise at all. The destroyer and the creator folded into one. We are a long way from the simple question we started with: why is the night sky dark? And yet every answer has pulled us deeper into the same story. The darkness is not empty. It is structured, it is active, it is filled with invisible matter, threaded by quantum fluctuations, organized into a cosmic web, punctuated by objects so extreme they break our best equations. And all of this, every galaxy, every filament, every black hole, every photon of ancient light captured by Webb, is moving toward the same destination, the same ultimate fate, a fate written not in fire but in cold, in silence, in a darkness so complete it makes the night sky we started with look blazing by comparison. Everything ends. That's not pessimism, that's physics. Every star that has ever burned, every galaxy that has ever spun, every black hole that has ever consumed a neighboring world, all of it is moving, right now, toward a final state of absolute stillness, a darkness so complete, so permanent, and so total that the word dark barely does it justice. But here's what I find remarkable about this story. The end of the universe is not a single event. It is a journey, a long, strange, almost incomprehensibly drawn-out process with distinct chapters, each one more alien than the last. And when you lay out that full timeline, from today all the way to the last possible moment of anything resembling activity in the cosmos, you realize that the universe we currently live in, with its blazing stars and spinning galaxies and churning black holes, is not the normal state of things. It is a brief, brilliant, wildly unlikely exception to a much longer story of darkness and cold. Cosmologists have a name for this full timeline. They call it the 5 Ages of the Universe, a framework developed by physicists Fred Adams and Gregory Laughlin in their 1999 book of the same name. Let's walk through it together, and I want you to hold on to something as we do. Every single number I'm about to give you is based on real physics, real observations, real calculations. This is not speculation. This is where the science currently points. We are living right now in what Adams and Laughlin call the stelliferous era, the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited, and it will end somewhere around 100 trillion years from now, when the last stars finally burn out. 100 trillion years. That number is so large it resists comprehension. The current age of the universe is about 13.8 billion years. 100 trillion is roughly 7,000 times larger than that. We are, cosmically speaking, in the very early morning of the stelliferous era. The universe is young. The stars are burning brightly. This is the golden age, and we are living in it. But even within this age, the universe is already changing in ways that point toward the darkness ahead. Star formation, the process by which clouds of gas collapse under gravity to ignite new nuclear furnaces, is slowing down. It peaked about 10 billion years ago, at a time astronomers call cosmic noon, when the universe was forming stars at roughly 10 times the rate it does today. Since then, the rate has been declining steadily as the available supply of cold, dense gas, the raw material for new stars, gets used up, blown away by stellar winds and supernova explosions, or locked up inside dead stellar remnants. The stars being born today are, on average, smaller and dimmer than those born at cosmic noon. The universe's star-forming productivity is winding down, not dramatically, not visibly on human timescales, but the trend is clear and measurable, confirmed by observations from telescopes, including Hubble and Webb. The stelliferous era is not eternal. It has a clock, and that clock is running. when the last star finally exhausts its fuel, and the last stars to go will be the smallest, dimmest, most miserly red dwarfs, burning their hydrogen so slowly and carefully that some of them will last for trillions of years. The universe will enter what Adams and Laughlin call the degenerate era. This age will be dominated not by burning stars but by their corpses. White dwarfs, the dense cooling remnants of stars like our Sun, roughly the size of Earth but containing the mass of an entire star, will be the most common objects in the universe. Alongside them will be neutron stars, the ultra-dense remnants of more massive stars that exploded as supernovae, and of course black holes. These objects are extraordinarily long-lived. A white dwarf, left completely alone with nothing to feed it, will simply cool over unimaginable timescales, fading from white to yellow to orange to red to a final state sometimes called a black dwarf, a cold, dark, inert lump of crystallized carbon and oxygen floating silently in space. The universe will be full of them, countless trillions of invisible, lightless spheres, remnants of everything that ever burned. But here's something remarkable that might happen during this era, if we wait long enough. Quantum mechanics allows for an extraordinarily rare but theoretically possible event: proton decay. The proton, one of the two types of particle making up atomic nuclei, the foundation of all ordinary matter, may not be perfectly stable. Certain extensions of the standard model of particle physics predict that protons have an incredibly long but finite lifetime, eventually decaying into lighter particles through processes mediated by exotic hypothetical particles. The predicted proton lifetime in the most conservative versions of these models is somewhere around 10 to the power of 34 years, a number so vast it makes the current age of the universe look like a rounding error. We have never observed proton decay. Experiments like the Super Kamiokande detector in Japan, a tank of 50,000 tons of ultra-pure water buried deep underground, surrounded by thousands of light sensors, watching for the faint flash of a proton decay, have been searching for it for decades and found nothing so far. This has actually ruled out some of the simpler theoretical models, but if protons do eventually decay, then during the degenerate era, all ordinary matter, every white dwarf, every neutron star, every cold dark rock drifting through the void, will simply dissolve. Not explode, not collapse, just quietly come apart, atom by atom, proton by proton, until nothing made of ordinary matter remains. The universe will have eaten itself from the inside. Whether or not proton decay occurs, the next era belongs entirely to black holes. Adams and Laughlin call it, simply, the black hole era. By this point, we're talking timescales beginning around 10 to the power of 40 years from now, stretching to perhaps 10 to the power of 100 years. The universe will be almost inconceivably empty. No stars, no planets, no gas clouds, possibly no ordinary matter at all, if proton decay has done its work. The only objects of any significance will be black holes of various sizes, floating in an expanding, cooling, darkening universe, separated by distances so vast that the probability of any two of them ever interacting becomes vanishingly small, and yet even the black holes are not permanent. Remember Hawking radiation, that slow, steady quantum evaporation we discussed in Part 5. In the black hole era, with nothing left to feed the black holes and keep them massive, Hawking radiation becomes the dominant physical process in the universe. The black holes shrink, imperceptibly slowly at first, then faster as they get smaller, because smaller black holes radiate more intensely than larger ones. Eventually, each black hole reaches a critical size and releases its remaining mass in a final burst of high-energy radiation. One by one, the last objects in the universe wink out. The largest supermassive black holes go last, after timescales that require numbers with hundreds of digits to express. And when the final one evaporates, the black hole era ends. What remains is almost nothing, a thin, cold, expanding gas of photons and leptons, electrons, positrons, neutrinos, spreading through a universe so vast and so empty that the average distance between any two particles is larger than our entire observable universe is today. The temperature of the universe approaches absolute zero asymptotically, never quite reaching it but getting closer with every passing eon. This final age is called the Dark Era, and it may last, quite literally, forever, or at least until something we currently have no framework to predict brings it to a close. Now, I want to pause here because I think there's something important to sit with before we continue. This picture, stars dying, matter decaying, black holes evaporating, the universe cooling toward absolute stillness, sounds on the surface like an almost unbearably bleak story. And I understand why. There is something in us that recoils from the idea of permanent, irreversible endings. We are creatures who build, who love, who create meaning. And the idea that all of it, every cathedral, every symphony, every act of kindness, every civilization that might ever arise anywhere in the cosmos, is ultimately just a temporary arrangement of atoms in a universe trending toward maximum disorder, feels like it should be devastating. But I want to offer you a different frame. Not a false consolation, not a manufactured silver lining, just a different way of seeing the same facts. The reason we exist at all, the reason any complexity exists in the universe, is precisely because the universe began in a state of extraordinarily low entropy, extraordinarily high order, and has been winding down ever since. That winding down process, that slow release of energy as the universe moves from order to disorder, is the engine that powers everything. Stars burn because they are dissipating the gravitational potential energy of collapsing gas clouds. Life metabolizes because it channels the energy flowing from the sun into chemical order. Thought happens because neurons use the energy gradient between oxygen-rich blood and cellular metabolism to maintain structured patterns of activity. We are not fighting against entropy. We are entropy's most elaborate and beautiful expression. The darkness at the end is not the negation of the light. It is what makes the light possible, meaningful, and finite in a way that gives it weight. The physicist Brian Greene, in his book The Fabric of the Cosmos, puts it something like this: the universe is a story being told in the language of physics, and every chapter, every era, every age has its own kind of beauty. We happen to be reading one of the most spectacular chapters. That's not nothing, that's everything. But wait, and I mean this genuinely, wait, because the story of the universe's ultimate fate is not as settled as I may have made it sound, and the uncertainty hiding inside it is in some ways the most fascinating part. The scenario I just described, the 5 ages, the slow cooling, the Hawking evaporation, the dark era, is the prediction of our current best models, assuming dark energy remains constant and the universe continues expanding at its current accelerating rate. But there are alternative scenarios, and some of them are considerably more violent. One possibility is called the Big Rip. If dark energy doesn't stay constant, if it grows stronger over time, as some theoretical models allow, then the expansion of the universe could eventually accelerate so dramatically that it overcomes not just the gravity-holding galaxy clusters together, but the gravity-holding individual galaxies together, then the gravity-holding solar systems together, then the electromagnetic forces holding atoms together. In the final fraction of a second before the Big Rip, even atomic nuclei would be torn apart. Space itself would be ripped to shreds. Every structure in the universe, from the largest supercluster to the smallest proton, destroyed simultaneously in a catastrophic, instantaneous unraveling. Current observations suggest dark energy is consistent with a cosmological constant, a fixed, unchanging value, which would point away from the Big Rip. But our measurements are not precise enough to definitively rule it out. The difference between a calm, slow fade and a violent, Total destruction could come down to the precise value of a single parameter we haven't pinned down yet. Another possibility is called vacuum decay, and this one is, without question, the most unsettling scenario in all of cosmology. It stems from the nature of the Higgs field, the quantum field that gives fundamental particles their mass. Measurements of the Higgs boson's mass, confirmed after its discovery at CERN's Large Hadron Collider in 2012, suggest that our universe may exist in what physicists call a metastable vacuum state. Not the lowest possible energy state, but a local minimum, stable enough to have lasted 14 billion years, but not the true ground state of the field. If that's correct, then somewhere in the universe, at any moment, a quantum fluctuation could nucleate a bubble of true vacuum, a region where the Higgs field drops to its actual lowest energy state. The walls of that bubble would expand outward at the speed of light. Inside the bubble, the laws of physics would be completely different. The masses of particles would change. The forces governing chemistry and nuclear physics would be altered, and nothing resembling atoms, molecules, stars, or life could exist. The bubble would be invisible and undetectable until the instant it hit you. There would be no warning, no time to react. The universe as we know it would simply stop, replaced by something unrecognizable, propagating outward at the speed of light. The good news, such as it is that if this were going to happen soon, it almost certainly would have happened already somewhere in the observable universe, and we would likely have seen some evidence of it. The long lifetime of our vacuum suggests it is at least reasonably stable, but reasonably stable and perfectly stable are very different things on cosmological timescales. I realize I've just walked you through some genuinely heavy territory, the end of the stars, the decay of matter, the evaporation of black holes, the possible violent death of the universe itself. And I don't want to leave you in the dark, figuratively speaking, without giving you the thing that for me personally makes all of this not just bearable but genuinely awe-inspiring. Here it is. You are made of atoms forged in the hearts of stars that exploded before our sun was born. The calcium in your bones was manufactured in a supernova. The iron in your blood was produced in the core collapse of a dying star. The carbon in your DNA was built up through nuclear fusion reactions in stellar interiors over billions of years. You are, in the most literal and scientifically accurate sense, made of the universe looking at itself. And in a cosmos trending toward darkness, in a universe where complexity is temporary, where stars are mortal, where even black holes eventually fade, the fact that matter arranged itself into something capable of asking questions about its own origin and destiny is, by any reasonable measure, the most astonishing thing that has ever happened. The darkness is coming, eventually, on timescales so vast they make our entire cosmic history look like a single heartbeat. But right now, in this extraordinarily unlikely moment, there is light, and there are minds to see it. And if you're the kind of person who looks up at the night sky and feels something stir inside you, subscribe to the channel and give this video a like. We are just getting started, and the next videos go even further into the unknown. So far in this journey, we've moved outward. We've zoomed from the night sky above your head to the edge of the observable universe. We've mapped the cosmic web, stared into black holes, and watched the universe age all the way to its final darkness. But now I want to take you in the opposite direction. Not outward, inward, down to the smallest possible scales, down to the level where space itself stops being the smooth, continuous fabric we imagine it to be, and starts behaving in ways that make even professional physicists uncomfortable. Because here's the thing about the darkness of space that nobody talks about enough. It isn't passive, it isn't simply the absence of something. At the deepest level of physical reality, the vacuum, the emptiness between particles, between atoms, between galaxies, is one of the most energetic, dynamic, and frankly bizarre environments in the entire universe, and our best attempt to calculate exactly how energetic it is produced a number so catastrophically wrong that it has been called, without much exaggeration, the single worst prediction in the history of science. That failure is not a footnote. It is a flashing neon sign pointing directly at the deepest gap in our understanding of reality. And closing that gap would almost certainly require a revolution in physics comparable to the ones triggered by quantum mechanics and general relativity in the early 20th century. Let's build this up carefully, because the details matter and the payoff is worth it. Quantum field theory, the framework that describes all known fundamental particles and forces except gravity, tells us that every type of particle corresponds to a quantum field permeating all of space. The electron field, the photon field, the quark fields. These are not metaphors, they are real mathematical objects whose vibrations and excitations produce the particles we observe. An electron is, in this framework, a localized excitation of the electron field. A photon is a ripple in the electromagnetic field. Reality, at its deepest accessible level, is fields all the way down. Now, quantum mechanics has a fundamental principle called the Heisenberg uncertainty principle, which places hard limits on how precisely you can simultaneously know certain pairs of physical quantities. The most famous version involves position and momentum. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving, and vice versa. But there's an equally important version involving energy and time. The more precisely you try to define the energy of a system over a very short time interval, the more uncertain that energy becomes. The consequence of this for quantum fields is profound. A quantum field cannot simply sit perfectly still at zero energy. That would mean knowing both its value and its rate of change with perfect precision simultaneously, which the uncertainty principle forbids. So even in its lowest possible energy state, what physicists call the vacuum state or ground state, a quantum field is constantly fluctuating. It has what's called zero-point energy. It can never be completely quiet. Every quantum field in nature has this zero-point energy. And since quantum field theory contains a large number of distinct fields, one for each type of particle and force, and since those zero-point fluctuations extend across all of space in all directions, the total energy of the vacuum should be the sum of the zero-point energies of all quantum fields integrated across all of space. When you do that calculation, even in a simplified, rough version, you get a number, a specific finite number for the energy density of the vacuum. And then you compare it to the actual measured energy density of dark energy, the observed value from our cosmological observations of the accelerating expansion, and you find that the two numbers disagree. Not by a little, not by a factor of 2 or 10 or even a million. They disagree by a factor of approximately 10 to the power of 120. Let me try to give you a sense of what that discrepancy actually means, because rattling off large exponents doesn't really convey the true magnitude of the problem. The observable universe contains roughly 10 to the power of 80 atoms. That's the total number of atoms in everything, every star, every planet, every gas cloud, every grain of dust, across the entire 13.8 billion light-year span of everything we can observe, 10 to the power of 80. The discrepancy between the theoretical vacuum energy and the observed dark energy is 10 to the power of 120. That means the mismatch between our best theory and our best observation is a factor larger than the total number of atoms in the observable universe by 40 powers of 10. Our theoretical calculation overshoots the observed value so catastrophically that if dark energy were actually as strong as the vacuum energy calculation predicts, the universe would have expanded so violently in its first fraction of a second that no matter, no galaxies, No stars, no atoms, and certainly no human beings would ever have had time to form. The universe would have been ripped apart before it began. The fact that we exist at all means the theoretical calculation is wrong. Dramatically, catastrophically, inexplicably wrong. Physicists call this the cosmological constant problem. Some call it the vacuum catastrophe. And despite decades of serious effort by some of the most brilliant minds in theoretical physics, nobody has a fully satisfying solution. There are approaches, supersymmetry, which pairs every known particle with a heavier partner and whose contributions to vacuum energy would partially cancel each other out, was a leading candidate for decades. But the Large Hadron Collider has searched extensively for supersymmetric particles and found none at the masses where they were most expected. That doesn't rule supersymmetry out entirely, but it has significantly dampened enthusiasm for it as a solution to the cosmological constant problem specifically. Another approach involves what's called the anthropic principle, the argument that we observe the value of dark energy we do because if it were much larger, the universe would have expanded too fast for galaxies and stars to form, and there would be nobody here to measure it. In a framework called the multiverse, where vast numbers of universes exist with different values of physical constants, observers will inevitably find themselves in one of the rare universes where the constants are compatible with complexity and life. The cosmological constant problem dissolves not because we can calculate the right answer, but because we understand why the only universes we could ever observe are the ones with small dark energy values. This argument was made quantitatively by Steven Weinberg in 1987, before the accelerating expansion was even discovered, and he correctly predicted that if the cosmological constant existed, it would be small but non-zero, in a range that would allow galaxy formation. When the accelerating expansion was confirmed in 1998, Weinberg's prediction turned out to be roughly right. That is either a stunning theoretical success or a deeply unsatisfying non-explanation, depending on your philosophical disposition. Many physicists find anthropic reasoning profoundly uncomfortable. It feels like giving up, like saying the universe is the way it is because if it weren't, we wouldn't be here to notice. Technically true, possibly even correct, but not the kind of mechanistic, predictive understanding that physics has always aspired to. The tension between quantum mechanics and gravity runs even deeper than the cosmological constant problem. And to understand why, I want to take you to the very edge of what physics currently knows, a place called the Planck, named after Max Planck, the German physicist who first introduced the concept of energy quantization and effectively launched the quantum revolution in 1900. The Planck scale refers to the regime where both quantum effects and gravitational effects become simultaneously important. It corresponds to length scales of about 1.6 times 10 to the power of negative 35 meters, roughly 20 powers of 10 smaller than a proton. At these scales, the smooth spacetime described by general relativity should dissolve into something else, some quantum structure of space and time that our current theories cannot describe. What does space look like at the Planck scale? We genuinely do not know. General relativity treats space-time as a smooth, continuous, four-dimensional fabric that can be curved by mass and energy. Quantum mechanics treats everything else as discrete, probabilistic, and subject to uncertainty. Combining them produces infinities and inconsistencies that signal a breakdown of our theoretical frameworks. The theory that would successfully unify quantum mechanics and general relativity, a theory of quantum gravity, is widely considered the deepest open problem in fundamental physics. Several candidate frameworks exist. String theory proposes that all fundamental particles are actually tiny, vibrating one-dimensional strings, and that their different vibrational modes produce the different particles we observe. It naturally incorporates gravity alongside the other forces and avoids certain mathematical infinities, but it requires extra spatial dimensions, typically 6 or 7, curled up at scales too small to observe, and it has so far produced no unique testable predictions that have been confirmed by experiment. Loop quantum gravity takes a different approach, quantizing space-time itself, treating space as made of discrete chunks called spin networks, with area and volume coming in minimum units rather than being continuously divisible. It makes different predictions from string theory and is more directly anchored to the mathematical structure of general relativity, but it also lacks confirmed experimental predictions. Both frameworks, and several others, remain works in progress. The theory of quantum gravity, whatever form it ultimately takes, will almost certainly transform our understanding of the very early universe, of what happens inside black holes, of what the Planck scale structure of the vacuum actually is, and perhaps of the cosmological constant problem itself. It is the next great revolution in physics, waiting to happen, and nobody knows when or from which direction it will come. Now, here's where all of this quantum strangeness reconnects to the darkness we started with, because the vacuum energy, the zero-point fluctuations, the quantum structure of empty space. These aren't abstract theoretical concerns floating in some rarefied corner of physics. They are the foundation of the darkness you see when you look up at the night sky. The dark energy accelerating the expansion of the universe. The force pulling galaxies apart, stretching the cosmic web thinner with every passing billion years, ensuring that the universe ends in cold and darkness rather than fire and collapse, is at its heart a quantum phenomenon. It is the energy of the vacuum, the restless, unavoidable, irreducible activity of quantum fields that cannot be switched off, cannot be shielded, and cannot be explained away. The darkness between the stars is not simply the absence of light. It is a quantum field in its ground state, humming with zero-point energy, pushing outward on the fabric of space in every direction simultaneously. The fact that it is pushing so gently, so incomprehensibly gently compared to what our equations predict, is either the most extraordinary fine-tuning in nature or a sign that our equations are missing something fundamental about the relationship between quantum mechanics and the geometry of space-time. Either way, the darkness is telling us something. It has been telling us something for as long as human beings have looked up and noticed it. And the message, translated into the language of 21st century physics, is this: you do not yet understand what nothing is, and here's what I find most extraordinary about that message. The fact that we can receive it at all, that we can look at the darkness, measure it, build detectors for it, calculate its properties to extraordinary precision, and then recognize clearly and honestly that our calculations are wrong, that is not a failure. That is the scientific method working exactly as it should. Every wrong answer in science is a treasure map. Every discrepancy is an arrow pointing toward deeper truth. The cosmological constant problem is not a crack in the foundation of physics. It is a door. And on the other side of that door is a theory of reality, more complete, more beautiful, and more strange than anything we currently know. We just haven't opened it yet. Before we get to part 8, I want to leave you with one more thought that connects all of this quantum darkness to the very human experience of looking up at the night sky. Every photon of light you have ever seen, every ray of sunlight, every glimmer of starlight, every flash of lightning began as a quantum event. An electron in an atom dropped from a higher energy state to a lower one, and the energy difference was released as a photon, a quantum of light, the minimum possible unit of electromagnetic radiation. And every time that photon traveled through space toward your eye, it traveled through the quantum vacuum we've been discussing, that churning sea of zero-point energy and virtual particles. It interacted with it, was shaped by it, was in some subtle sense influenced by it at every step of its journey. The light you see has been shaped by the darkness it traveled through. We've traveled a long way together. We started with a simple question: why is the night sky dark? And that question pulled us through the accelerating expansion of the universe, through invisible matter woven into every galaxy, through the largest structures ever mapped, through the violent hearts of black holes, through the ultimate fate of everything, and all the way down to the quantum trembling of empty space itself. We've covered billions of years in every direction. We've stared into the deepest darkness physics can describe. And now, before we close this chapter, I want to ask the question that I think has been quietly sitting underneath all of it, the one that makes all of this feel personal rather than abstract, the one that for many people is the real reason they look up at the night sky in the first place. Are we alone in it? Let's start with the numbers because they are genuinely staggering. Our Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. For a long time, we didn't know whether most of those stars had planets. That changed dramatically in 2009 when NASA launched the Kepler Space Telescope, a spacecraft designed to stare at a single patch of sky containing roughly 150,000 stars and watch for the tiny periodic dimming caused by a planet passing in front of its host star. What Kepler found over its 9 years of operation reshaped our understanding of the cosmos entirely. Planets are not rare. They are not exceptions. They are the rule. Kepler data confirmed the existence of thousands of exoplanets and suggested that, statistically, virtually every star in the galaxy hosts at least one planet. Many host several. Further analysis suggested that roughly 1 in 5 Sun-like stars has at least one roughly Earth-sized planet orbiting in the habitable zone, the region where liquid water could exist on the surface. In our galaxy alone, that means somewhere in the range of 40 billion potentially habitable worlds, 40 billion, around just the Sun-like stars. When you factor in red dwarfs, which are far more numerous, the number climbs even higher. Then multiply that by the hundreds of billions of galaxies in the observable universe. The arithmetic produces numbers so large they become almost meaningless. The number of potentially habitable planets in the observable universe likely exceeds the number of grains of sand on every beach on Earth, by a lot, and yet as far as we can tell, we have not heard from a single one of them. This is the Fermi Paradox, named after the physicist Enrico Fermi, who reportedly posed the question over lunch at Los Alamos in 1950. If the universe is so vast, so old, and so full of potentially habitable worlds, where is everybody? The Milky Way is about 13 billion years old. Our Sun formed roughly 4.6 billion years ago, meaning there are stars in this galaxy that are 2, 3, even 4 times older than ours. If life arises with any reasonable probability on habitable planets, and if even a small fraction of civilizations develop technology and the impulse to explore or communicate, then some of those civilizations should have had billions of years head start on us. A sufficiently advanced civilization, even traveling at a tiny fraction of the speed of light, could theoretically colonize the entire Milky Way in somewhere between 10 million and 100 million years. That sounds like a long time. On a galactic timescale, it is barely a blink. And yet the galaxy appears empty. Our radio telescopes, including the decades-long effort of the SETI Institute, the search for extraterrestrial intelligence, have been scanning the sky for artificial signals since Frank Drake pointed a radio telescope at 2 nearby stars in 1960. 60-plus years of listening, thousands of hours of telescope time, sophisticated signal processing systems capable of detecting an artificial transmission from across the galaxy, and the result has been with one tantalizing exception we'll get to in a moment: silence. Complete, unbroken, maddening silence. The Fermi paradox has spawned dozens of proposed solutions, each one revealing something different about how we think about life, intelligence, and the nature of the universe. Let me walk you through the most significant ones, because each of them connects back to the darkness in a way that gives me chills. The first category of solutions involves what's called the Great Filter, an idea developed by economist Robin Hanson in 1998. The Great Filter is a hypothetical barrier, somewhere along the path from simple chemistry to spacefaring civilization, that is extraordinarily difficult to cross. Something that filters out the vast majority of would-be civilizations before they reach the point of being detectable across interstellar distances. The terrifying question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, if the hard step was something in our past, like the origin of life from chemistry, or the development of complex eukaryotic cells, or the emergence of multicellular life, then we might be genuinely rare, perhaps extraordinarily, almost miraculously rare. The silence of the cosmos would make sense not because civilizations destroy themselves, but because getting to our level of complexity was a lottery with nearly impossible odds, and we got lucky. The darkness of the cosmic radio spectrum would be, paradoxically, good news for humanity's future. But if the filter is ahead of us, if there is something that virtually all technological civilizations encounter and fail to survive, some threshold that has wiped out every civilization that came before us and will likely wipe out us as well, then the silence is a warning, a terrifying one. The empty sky is not evidence of our rarity, it is evidence of our future. And here's the detail that makes this genuinely unsettling: the discovery of life, even simple microbial life, anywhere else in the solar system would be, counterintuitively, very bad news, because it would push the filter forward. If life arose independently on Mars or in the subsurface oceans of Europa or Enceladus, then the origin of life is apparently not that difficult, which means the filter isn't in our past. It's ahead. The second major category of solutions is in some ways even stranger. Maybe the silence isn't silence at all. Maybe we're simply not listening in the right way, or not capable of recognizing what we're hearing. Think about it from the other direction. Imagine a civilization 1 million years more technologically advanced than us. We can barely conceive of what they might be doing, what forms of communication they might use, what their goals and motivations might look like. Would they be broadcasting radio waves? Radio is a technology we developed in the late 19th century. It might be the cosmic equivalent of smoke signals, a brief, primitive phase of communication that advanced civilizations pass through quickly and then abandon for something far more efficient and undetectable to us. Some physicists have suggested that truly advanced civilizations might communicate using neutrinos or gravitational waves or quantum entanglement, or methods we haven't even theorized yet. We would have no way of detecting any of those with our current technology. The universe could be filled with conversations happening in channels we don't know exist, in languages we couldn't pass even if we intercepted them. There is also the possibility, deeply unsettling in its own way, that advanced civilizations deliberately go silent, that there is something out there, some danger, some predatory dynamic on the cosmic scale that makes broadcasting your presence extremely dangerous. The dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his novel of the same name, proposes that the universe is like a dark forest full of hunters, every civilization aware that announcing itself risks destruction, and so every civilization stays silent, watching, waiting, afraid. The darkness of space would be not an absence of life, but a consequence of it. every civilization hiding from every other in a cosmic standoff of mutual silence. It is a deeply fictional framing, but the underlying logic is not entirely without scientific basis. A civilization capable of crossing interstellar distances would likely be capable of causing extinction-level damage to another world, and the asymmetry of information, not knowing whether a detected civilization is friend or threat, might rationally favor silence over contact. Now, that tantalizing exception I mentioned. On August 15, 1977, an astronomer named Jerry Emmon was reviewing data from Ohio State University's Big Ear radio telescope as part of a SETI survey. He noticed a signal in the printout so striking, so anomalous, so unlike any known terrestrial or natural source that he circled it with a red pen and wrote a single word in the margin, "Wow." The signal, now known simply as the WOW signal, lasted for 72 seconds, matching the expected duration of a transmission from a fixed point in space as the Earth's rotation swept the telescope beam past it. It appeared to originate from the direction of the constellation Sagittarius. It had the precise characteristics, frequency, bandwidth, intensity that SETI researchers had theoretically predicted an artificial interstellar transmission might have. It was, by every observable measure, exactly what a signal from another civilization should look like. It was never detected again. Dozens of follow-up observations, using increasingly sensitive equipment over the following decades, found nothing. In 2016, a team of researchers proposed that the signal might have been caused by a comet or hydrogen cloud passing through the telescope's field of view, a natural explanation. Not everyone in the field is convinced. The debate continues. The WOW signal is a single data point. It proves nothing, but it has never been fully explained away either. It sits in the history of SETI like a crack in a wall, not large enough to see through clearly, but impossible to ignore. Here's where all of this circles back to the darkness, and I mean that not just as a metaphor but as hard physics. Remember what we established in part 1. The observable universe is bounded. There is a cosmological horizon, beyond which light has not had time to reach us, and dark energy is pushing that horizon outward in an accelerating universe. No, wait. It's actually shrinking the number of galaxies we can ever reach, as more and more cross beyond our ability to contact them. That means any civilization beyond a certain distance is not just far away. It is permanently, irreversibly unreachable, not because of our technological limitations, but because the universe itself is expanding faster than any signal, any ship, any message they could ever send can travel to close the gap. We are, in a very literal sense, islands. Every galaxy group isolated by the accelerating expansion, cut off from the rest of the universe on timescales of tens of billions of years. If there are other civilizations in distant galaxy clusters, civilizations that might have answers to the questions we've been asking throughout this entire video, they are already beyond our reach. The darkness between us is not a distance to be crossed. It is a boundary written into the laws of physics, and perhaps that is the most profound answer to Olbers Paradox that we could possibly give. The sky is dark not just because the universe is finite in age, not just because it's expanding, not just because the light from distant stars hasn't reached us yet. The sky is dark because the universe is structured in a way that enforces isolation. That builds walls of space-time between islands of light. That gives each civilization, if there are others, a finite window of time and a finite reach. Before the darkness closes in, we are not at the center of the universe, but we might be, in the only way that ultimately matters, alone in our corner of it. And yet, I keep coming back to this. And yet here we are, thinking about it, feeling it, building telescopes the size of the Earth to photograph the shadow of a black hole, sending spacecraft beyond the edge of the solar system carrying golden records, engraved with the sounds of Earth, whale song, thunder, a mother's first words to her child. Just in case something out there finds them someday, we are a civilization that has existed for the blink of a cosmic eye, on a pale blue dot orbiting an ordinary star in the outer arm of one of hundreds of billions of galaxies, in a universe trending toward cold and darkness on timescales we cannot truly imagine. And we looked up. We asked why. We built instruments to find out. We shared what we learned with each other, across generations, across cultures, across centuries, each generation handing the torch of curiosity to the next. That is not a small thing. In a universe as vast and as dark and as old as this one, the emergence of minds capable of understanding it, even partially, even imperfectly, is, by any honest reckoning, the most extraordinary thing we know of. The darkness is real. The isolation may be real. The eventual silence of the cosmos is written into its physics. But right now, in this brief, blazing, wildly unlikely moment, there is light, there are questions, there are people like you, staying curious, looking up, refusing to stop wondering. That is enough, more than enough. That is everything. The universe is unimaginably vast. Our time in it is short. Let's make every question count.